Okay. Well, this is round two of Simon's talk. There was a lot of feedback from the first round, and so we're excited to be the second. And I'm sitting here so you don't think all the people are afraid to be near you.
Okay, thanks. Also, there's speaker today, and I bought some cake. So yeah, so 3 p.m. in the at the round table. Okay.
It's called the oval table. I got
Sorry.
reprimanded for calling it the round table by some professors. I know, that's what I said.
So yeah, so I spoke on the 8th of January about open science, and there was I made it sort of slightly provocative so that it would make some discussion, which it did. So so that was great. So this is the second part, and the second part, as I envisioned it, would be to empower you to make your research reproducible. So that's what I'm gonna aim to do. But I couldn't help myself. I'm also talking a bit about the history and stuff, different things. So let's get started. I can make this work. So what is the definition of reproducible research? Well, a research work is called reproducible if all information relevant to the work, including but not limited to text, data, and code, is made available, such that independent researcher can reproduce the results. So if you're a reviewer, for example, ideally you should be able to just go into a repository, click a button, compile everything, see all the figures. The figures are generated by the code from the data. That's the dream, right? Or if you're an independent researcher wanting to check the work, and one can just imagine what it would be like if that was true. Or what would it do to the way we produce research? How much more rigorous would we be in our analyses, and how much more transparent would it be? So, okay, so first of all, some definitions. What does it mean for something to be reproducible, to be replicable, robust, and generalizable? So if you're doing the same analysis on the same data, that's what's called reproducible. If you're doing the same analysis on different data, so that's replicable. So you replicate something by using the same analysis, but as a person who's done something before, but you get new data and you apply that analysis to that data. And then if you're doing a different analysis on the same data, then it's more robust. If you're doing a different analysis on different data, then that's generalizable. So this can be debated, what should we actually call reproducible or replicable? I think this is reasonable, and I think this is something we should adopt. So I'm mainly going to talk about reproducibility today. So it's important to note that reproducibility is not replicability. That's the most common misconception. I would have to argue that it is a misconception because some people use terms interchangeably. So reproducibility and replicability are the hallmarks of good science. So research is becoming more collaborative, transparent, and reproducible. And due to the growing dependence on data and compute-intensive research in all sciences, it's becoming more prominent. And there's also growing international and national efforts to mandate these practices and strive to develop infrastructure and tools to support reproducibility. So I'm going to show you some of this infrastructure and some of the tools. So universities and funders should soon, hopefully, have systems in place to assess the reproducibility scores or indexes of researchers. So the idea would be that you as a researcher would have a reproducibility index attached to your name. Scary, huh? This is not a reality yet, but it's something that's being discussed, Okay, so I'm going to start with a bang here and say that if your methods are not reproducible, you are not, in fact, doing science. I'm not sure what you're doing. You're playing around if you're advertising yourself. I'm not sure. But if you can't do the same analysis on the same data and get the same result, it's not science. I think that reproducibility is sort of like the minimum that we could demand of something that we are calling science. Does anyone know who that guy is? No, it's from an obscure Swedish movie in the 60s. Okay. Okay. So what do other people think? Is there a reproducibility crisis? Well, 52% of researchers seems to think that there is a significant crisis. And 38 think that it's a slight crisis, and 3% say that no, there's no crisis, and 7% don't know. What about radiology?
When is that from?
It's from Nature.
Date, because I guess this might change over time.
Right, true. I don't have the actual reference there. I can get it.
Good question, good question.
I was taking that survey, I would have trouble separating reproducibility from replicability.
Not anymore, though.
Right. So if we're taking this and you said, okay, if I give you the same data and you put it through the same algorithm, you get the same result, I think that most people would say, yeah, that happens all the time. So I'm thinking these people who are saying it's a crisis are thinking, doesn't mean someone else can reproduce the results. So I think this is a little huge survey.
So you're saying that it could be, we could say, is there a replicability crisis there?
I'm saying I'm in the 3% and everyone else is wrong.
Well, I think that if we replace it with a replicability crisis, this statistic gets even more alarming. I argue, but we can. I haven't gone into the exact details of how this survey was performed, but I do have the. I don't know why I didn't put it up. It's from Nature, obviously, but the date I can find.
I think there was a question.
Oh, sorry. Yeah.
No, I'm just wondering what the people are thinking that are responding here. Like, do they have this opinion based on their own data or based on like, you know, how, because I mean, you know, we get to review other people's papers, and so maybe based on that we think, yeah, that doesn't make any sense. But I'm just, was there anything in that article about what the opinions were based on?
It's from 2016.
Oh, thanks. Well, I guess, I mean, it's, of course, it all boils down to, like, what do we mean with reproducibility? How was this question asked? Is this, you're trying to reproduce someone else's data, someone else's results, or you're trying to reproduce your own? And if you're trying to reproduce your own, then I would think it's more alarming, because if you can't, it's one thing not to be able to reproduce someone else's stuff, right? Because that person might not have had good record keeping and might not have been working reproducing. But if you can't, if it's your own data, then I think it's more alarming. So sure, it's quite heavily, the interpretation of this statistic is heavily dependent on what specific question was asked and whether they mean reproducibility or replicability. Sure. And I don't have the details offhand here.
It was from the disciplines of biology, chemistry, earth and environmental, medicine, physics and engineering, and other. Most of them were biology. We found that physicists and chemists were most confident in the literature.
That's nice. So let's segue into radiology then. So in this study, they identified about 300,000 records, and they randomly, you can't go through that amount, obviously. So they randomly selected 300 of these, and they made some reproducibility, what they called reproducibility indicators. So this is also, again, very important. It depends on the specifics of this, of how what you call a reproducibility indicator. So this kind of surprised me that 5.6% had a date availability statement. So I would guess that this is mostly old stuff, right? I think everybody has data availability statements nowadays.
Yeah, but what is the statement?
Well, I covered that last time. The statement is that it's available upon reason or request to the author. And then there are studies that show that even if you request it from the author, you won't get it. So we could, again, we could dive into the specifics of the study, but I think that their conclusion is valid, even thinking about a large spectrum of how to interpret these reproducibility indicators. So one thing about reproducibility is that it's not, something isn't reproducible or not. It exists on a spectrum. So you'd say that a publication only is not reproducible. Well, you could argue that it is. I mean, you can read the methods section and you can perform the experiment and the analysis. If it's well described, what is even better is if you have publication plus code. Even better is if you have code and the data. Like, what are you going to do with the code if you don't have the data? It's, I mean, sure, it makes for a slightly more compelling argument, I suppose. And then linked and executable code and data, that, yeah, not everything has to be linked and executable these days. But over at the other end, we have the full reproducibility, where what I said before, that you can just, as a reviewer, you can within 15 minutes, like click a button, it drags the data from a repository, runs all the scripts, and you end up with the figures from the data. So what are the factors impacting reproducibility? Well, there are technical factors, human factors, study design and statistics, rewards and incentives, which can be subdivided into a lot more. So today I'm going to go through a few of these. So last time I focused a lot on fraud, which I think is an interesting subject. It's very juicy, sort of. And I made the case that data should be available because it enables what's called statistical forensics. So I talked about the Duke Potty disaster, where people were given cancer medicine based on their genetic testing, even though the guy had just falsified everything, and it wasn't found out until 10 years later, basically, and all the clinical trials were stopped. So having the data enables this forensics statistics. And this is gaining some traction. I'm not sure how current this is anymore with what's been going on, but there is pressure coming from funding agencies to make data more available. Okay, so how do you share data then? Well, there's just simply so many repositories where you can do this. You have the Open Science Foundation, Zenodo. You can upload several gigabytes without having to pay for an account or anything. Dataverse project is something from Harvard, where they make it very easy to deposit data and curate it. NIH has its own platform of doing this. And I just put up the red tape there because I think my first thought when sharing data, especially like images from patients, is like you have to be very careful with the legality of this stuff. But usually these platforms can also help you get in touch with the right people.
Is it ambiguous? You say shared data. I mean, there's raw data. Let's say you're doing it. I'll pick on Gary. Let's say you're doing an fMRI study. It's one thing. Even if you shared all the images, someone could say, "Well, I want the case-based data because I don't know what maybe the reconstruction algorithm is not." Or you showed them the final plots of the correlation functions and you shared that data. It's a very different thing. It's not clear what it is you're supposed to share. If it's really reproducibility, you're supposed to share, I guess, the raw data.
I suppose, yeah. Which in many cases is perhaps not feasible yet.
Or
not very useful.
Well,
it depends on the focus of the study, though, because if your paper is a reconstruction paper, obviously you need to share the raw data. But if your paper is just analyzing like images, that's enough to reproduce the results.
Well, I would think you still need the raw data because there's some algorithm that went into making the images out of the raw data. How do I know that that algorithm gets the same results each time? That's the definition of reproducibility.
Right.
I think it makes sense to limit it to this study. So if the study didn't do it, like, it's like that.
Yeah, I mean, where do you stop? I mean, where
Where do you draw?
with the
lines?
reproducibility? I don't know. That's highly field dependent, I would say, and depends on the study. I mean, can we take the reconstruction algorithms for granted in giving us an accurate image? Well, in some cases, I suppose. But if what we're presenting is a reconstruction algorithm, then perhaps that's important. There are practicalities involved as well, but these could potentially store a lot of raw case-based data. I mean, the amounts of storage available is quite big. Yeah.
Maybe in the future, if enough code is shared, you could use like someone else's reproducible algorithms, and then you wouldn't have to share the data before that step.
Oh, so you can, yeah, so there's standardized,
like
like,
reconstruction algorithms or something that used a standardized one that was already shared and proven you wouldn't need to share the raw data prior to that point.
sure. Well, I mean, that is the case with, there's images like Lena, for example, which used for like image. Yeah,
You can finish that. I have another. So,
Yeah.
yeah.
no,
I mean,
no, yeah.
First is like for data sharing. So Dryad is another very good.
Right, yeah, sorry.
And I think that data sharing might be kind of relatively easy compared to code sharing. Because data, yes, you can say, okay, I have the raw data, here's the process data, and you get, but code sharing is, I think, trickier because many times it involves many dependencies, and it's system-based, it's version-based. So I think that's I don't know if you have something separate for that.
Yeah, I'm glad you brought it up because I'm going to show you.
Code sharing is more difficult because even raw data, if you don't have the appropriate code to analyze, so probably you would need to provide the code, but most of the times code won't work just on anyone's computer.
I think that you're right, but I think that there are solutions to the problem of dependencies, and
Yeah.
I think that might be equivalent to the problem of like not having metadata attached to the data, because a lot of times when I've received other people's data, it's just like an Excel sheet, with like column headers that make no sense. Yeah.
Still hung up on this reproducibility, replicability.
Mhm.
Sometimes, if someone told me their data was reproducible, I should say, I don't care. What I want to know is if someone else did the experiment, did I get the same result? So, replicability is the one I care about, not reproducibility. Let's say someone's got a flawed algorithm, and every time they run it, get the same answer. That doesn't give me much comfort. What I really want to know is if someone else, if I did the experiment, I'm going to get the same results. Can I draw something from it?
Sure, I think, yeah, that's true. But I think in this presentation, I wanted to focus on something that you yourself can do.
Okay.
You can't force someone else to make the same experiment as you did. Maybe you can. I mean,
Well, in principle, you give them the tools to
Sure.
do it themselves.
So in order to replicate something, I guess the methods need to be reproducible. So one sort of needs the other, I guess.
Yeah, I mean, on that probably, I mean, that's why code sharing is important, so that the reproducibility part is part of that, I guess. Just checking, someone can check the code as well,
Yeah.
so to make sure things are.
Yeah. Yeah.
I mean, a lot of images are vendor supplied. So at some level, if you assume the vendor doesn't have random number generators in their recon or something like that, then you don't need to worry about the raw data. You need to worry about the DICOM images or whatever are available, and that you can do the same analysis for reproducibility. But I agree with Dan that reproducibility is kind of a stupid concept. I mean, I don't care if somebody can't reproduce their own results. What I care about is exactly what Dan said. that the concept that they alluded to in their paper can be done by other people, and you get the same answer. That is, something or other is being done. Now, of course, as somebody else said, if we're really, the paper is about the recon, then obviously you need the raw data. You need the step before the reproducible part of what you're publishing. So if you're publishing some vendors' EPI data for fMRI, which almost all of them are, then you don't need to have the raw data. You need to have the images because you trust that the vendor doesn't generate random images. Each time
Yeah,
it
sure. I
runs the
mean,
same thing.
at some it stops somewhere, right? So if there's like an FDA approved MRI scanner, then maybe that's enough, you know. But I don't think it's fair to say that reproducibility isn't important. I mean, how is I think reproducibility is a prerequisite of someone else being able to replicate it.
First level, obviously, but
Yeah. So
just say it's a low bar.
yeah, it's a low bar, and which is why I think it's important, and I think it's becoming a problem because things are just getting more complex and more compute heavy, and there are these secret little black box algorithms that nobody knows about everywhere. Yeah.
I might be mistaken, and I don't remember the table very well, but the table said method and data, not who's doing the experiment, right? So reproducible, even if I do it and it's not my paper.
Yeah,
With
I
the same
mean,
data,
yeah,
the same
if you do
method.
it on the same data, then
So
yeah.
that's still reproducibility. Yes.
Yeah.
If I am not able to rerun my code with my data, that's a huge problem.
Yeah, that's a little, I mean, I could write a program that statistical analysis that gives a p-value of 0.05. Okay? Totally reproducible because it's independent of the data you put into it. Okay, is that useful? Everyone who runs this program gets a p of 0.05. It's such a low bar that it's not meaningful.
Yeah.
I think it's more meaningful than when you're dealing with code, like this is not very clear that it will happen. Like it's a complicated problem.
I mean, it's not the only important thing. Obviously, there's like effect size and like what you're actually. You can have a useless method that's highly reproducible. It doesn't mean that it's good, right? It's just, you know.
I wanted to say one thing, that all of these have like different commitments on how long they will keep your data. Some of them are 10 years, some of them are 1 year, some of them are like for eternity. So if you're selecting one of these, check that out.
Yeah. So check the fine print. That's the red tape, I guess. So Stanford has its own, actually. Yeah, sorry.
Yeah, so I have a question regarding these websites you proposed before. I'm a computer scientist, so for me it's much easier to share code than it is to share data. And I usually have data sets like from the Alzheimer's Disease Neural Initiative, for example. And in the data terms and usage, it specifically says that it's not allowed to share the data. So would you say this is sharing data in that sense, or is that legal in a way?
I mean, it can
because
be
I don't
legal.
want to get in
It can
trouble.
be
But
legal. It depends. Yeah. From my understanding, it can be legal to share anonymized data.
okay.
I think in this case, you might not share the data from the initiative, but you can link, for example, where you took those data. For example, like I don't know, you use like a subject one of time point whatever and add data. You can link the actual what kind of subject you use, time point, so that someone can download the data from the admin, for example, dataset and rerun your code.
So I mean, ideally, what I was thinking is, if you go to the previous slide or 2 slides previously, I think you had this like left to right.
Yeah,
a couple of slides ago. So I think like for me, like going to linked and executable code and file and data could be feasible in a way if I could share the data, right? Like if I require someone to go through the admin thing and apply for everything, I think that's not feasible really to make it reproducible. So therefore, I was thinking,
why isn't it feasible? Is it too big? Is it?
I think they are quite restrictive in who they give the data to. So if you say I'm a reviewer for a paper, but I don't really work in, let's say, neuro image analysis, they will probably reject your request to get access to the data. Plus, if you submit, for example, to a conference, then you only have a couple of weeks to rerun the code anyway.
Sure, but I think that's the attitude that we need to change, I think.
We need to change the ethics as well.
Yeah, sure. I mean, that is the red tape thing, right? So what's legal actually? What can I share? Like, I have to be careful, right? And okay, so of course there's a feasibility.
There's someone on Zoom talking.
Someone on Zoom is trying to talk.
Oh,
Sorry, I just have a quick clarification back to the previous comment that Dan was making. Is it possible that your idea of linked and executable code is too strong of a condition? Because to me, if I read a paper and they say they did a Mann-Whitney test or whatever, and I have my own code to run the exact same test, to me, that is reproducibility, and I care whether or not that works. Whereas I might not trust their code. So I'm where is this idea of the exact same code coming from rather than repeating their methods exactly as stated? Because to me, I think the repeating their methods as stated is much more useful than rerunning someone's code. And it's not a new analysis. It's just, can you recreate their analysis?
sure. I think, I mean, running a Mann-Whitney test is something everybody knows how to do. But I think that as the methods get more complicated, you have a description of what they've done, what their algorithm does. But you as a reviewer, as an independent research, is not going to sit down and code that, whatever that algorithm is. And I think this example is taken from, with the linked executable, is taken from computer science, where you can have code that you need to compile, and it's often fails to compile because of dependency issues. But I think for something like a Mann-Whitney, everybody knows how to calculate it. It's in all the software packages. That's not an issue. But let's say like a machine learning algorithm or something more complex that you're not going to code yourself. Does that make sense?
It does make sense, but I still wonder, you know, even if it's machine learning, if I'm given the architecture, in theory, I should be able to take their data and their architecture and get out the same results. Whether or not I would want to put in that level of time is another question. But to me, that question is an important question that I think is part of reproducibility, and we shouldn't be forgetting it. Because it's like Dan said, I don't know if their code is just saying, no matter what the input is, spit out 1.5. And so I think there needs to be somewhere where their executable code also, like the creation of their algorithm also needs to be reproducible.
The creation of their algorithm, well, okay, so you mean actually compiling the executable?
Right. If their program isn't actually doing what they say it's doing, or is it based on what they say it's based on, that is a real problem. And I think that's more of a problem than does their executable code produce the same results. To me, I'm more worried about, is their executable code doing what they've told me their executable code is doing?
Okay, yeah, sure. But I think that, I mean, I guess having the executable, it's basically a matter of like time, how much time and effort someone would be willing to put into reproducing something. But imagine the case that imagine if everything would be full reproducibility. Imagine what that would do, how that would eliminate all the sloppy research that can be seen everywhere. Like just nobody is actually checking it. Nobody actually have to, but just the fact that someone would change everything.
I think that's just like saying, I wish people would stop faking their data. I mean, I would love to live in a world where nobody lies, but I don't think that is relevant, because we don't live in a world where nobody lies. We don't live in a world where people don't fake their data. We don't live in a world where people don't fake algorithms. I mean, you look at Theranos, right? If I had taken my data and I had taken the provided analysis that Theranos gave, I would have reproducibility. But if I had taken their data, taken what they said their algorithm was doing and tried to recreate it, that's not reproducible. And that's what I care about. So I think it's a moot point to say, does their executable code give the answer that I expect their executable code to give? Because that doesn't actually tell me anything.
Okay,
it's
so you're
nice
coming
to
to
check.
the fact that it needs to be replicable, not only reproducible.
No, it's not replicable because it's their same analysis or what they're reporting that they're doing. So it's not a different analysis. I'm not changing how the data is analyzed. I'm repeating exactly what they said they've done.
So you're not interested in transparent methods, or I don't understand what you're arguing there, really.
We can talk about it offline. It's fine.
Okay.
If you have the code and executable, you will be able to check if that's what they did, right?
That is true. I think just the executable is not of interest to me, but if I have their code and the executable, that is more of interest to me.
Sure. Let's see, I have 10 minutes left. It's going to be a part 3. It's never going to stop. Okay. So I looked for entries in the Stanford repository specifically from RSL. So how many entries do you think I found?
0.
0? It's a very cynical. Okay. Well, it was 1. But it was from the lab I'm a member of. So that was great. Yeah, but actually, when talking about Stanford, reproducible science has a great history at Stanford. So John Claerbout, I'm not sure how to pronounce his name, he introduced the idea of these reproducible practices in a Stanford exploration project, and they were working on geophysics research during the 90s. So this idea that you would have the data, the code, and everything, and you click a button and you get the same result, and then you call it reproducible. Also, Donald Knuth, he invented literal programming, Jupyter Notebook. He didn't create Jupyter Notebook, but he introduced the idea of literate programming, where you sort of intermix code with output and text. There is also a Stanford Data Science Center for Open and Reproducible Science, headed by these guys. And there's tons of resources on how to do this. And I just want to talk about something called sleuthing, which is, I think it's a really cool thing. So last time I talked about Keith Baggerly and Kevin Combs. They were the ones who did the statistical forensics to expose the potty disaster. There's also Data Colada. So I don't know how active these guys are right now, but they sort of, this guy, Yuri, he coined the term p-hacking, which we will discuss if we have time. But they uncovered the fraudulent behavior of people, of social psychologists like Dan Ariely and Francesca Gino. And then we have Retraction Watch, obviously, huge deal. This is from an image from a sleuth meeting in Prague. So this guy, he is responsible for 1,000 retractions. But we have to remember also that not all retractions are due to fraud. I mean, there can be, human mistakes as well. So yeah, I think that Data Retraction Watch, they have a list of Nobel Prize winners who've had retractions, and it's a long list. So mistakes happen also. Not everything is fraud. I also thought it was funny. I just Googled sleuth, and it turns out that it's a detective, but it's also a collective noun for a group of bears, which I wasn't aware. Okay, so let's sleuth. Can anyone spot what the problem is in this image? I've introduced a slight coordinate system.
Well, the replication of the
E4 and
galaxies.
F6 is
F7 and D3 are the thing.
Yeah. Yeah, so you found both.
Good.
Nice. So people do this, and people papers are retracted en masse because of these things. So if you find this funny and intriguing, you can get involved easily. Okay, so let's discuss. I think I need to go to the live demo actually.
Live demo.
Yeah, I just wanted to do this. Wait, so misunderstanding statistics is a problem. So that's why I'm going to do a review of all the statistics. No, I'm just kidding. No. We had a talk. We had a talk last week. We have RSL biostatisticians that we can contact if we're unsure of anything. We can just double check with them if you're unsure. So this is the problem that I wanted to address. So poor records keeping and poor sharing of methods. So poor records keeping. Well, now I feel like sort of like Robert Jordan telling depressed people to clean the room. Like it's very like, of course you should have an organized folder structure. I mean, it's, I don't know who doesn't, but I think that's a key component of any project is just good records keeping, right? So literate programming, which I discussed earlier, not discovered, but invented here at Stanford. So it's a computer program that is given as an explanation of how it works in a natural language, interspersed with embedded code and outputs. So modern examples are R Markdown for statistics and Jupyter Notebooks, which is also, I think, has everybody used a Jupyter Notebook? Nobody is saying it. Yeah, okay. Yeah, so I'm going to skip this. So is literate programming enough? No, it is not. Sorry. So this is a large-scale study about the quality and reproducibility of these notebooks. So they took about 1 million unique notebooks and found from a bunch of GitHub repositories. And out of slightly less than that number, they attempted executions. Only 24% executed without error, and only 4% produced the same result. So that's, yeah. Yeah.
I haven't really read this article, but like the number they were trying to test is very, very big. And I'm just questioning like how carefully they actually look at the requirements that they had to do to run without errors the notebook, because that's not as like trivial. Whoever programs and codes and have GitHubs knows that errors are very common, and they're not just because maybe someone made a mistake. It's probably because you didn't actually read a lot of the things, the fine print that should be able to.
True. And maybe a lot of these GitHub repositories as well were not created with the intent of sharing the code or the code being reproducible, but as a means of backup for the person who wrote it. And also GitHub, because GitHub is if you want to keep it secret, you need to pay, right? So yeah, so I agree. It's not maybe it's not a fair comparison.
I'm less skeptical about running without errors, but more about if it runs without errors, only 4% produce the same result.
Sure.
So even when all things are going proper, that's why I have an issue with.
Yeah, I think they could have done the approach that the other large data dredging sort of data mining thing was. They could have identified these and then just picked 100 at random and then went through them or something like that. That would be another approach.
Yeah, I'm also confused. What does the same result mean? Yeah, like what's the result they're comparing?
So if I give you a Jupyter notebook, it's usually, it has a code and then it has the outputs that it had when I ran it.
Yeah.
So then if you run it again, you would ideally get the same result, right?
Yeah, but then similarly, it's like if people are making changes to the code, not rerun. Like, if these aren't meant to be, if these are just GitHub repositories that someone's using for themselves, and they're changing the code and not rerunning that cell, but they know that I don't know. It doesn't seem like that.
Yeah, it's a bit of an unfair comparison, maybe. These GitHub repositories might not be made with the intent of sharing code. Fair. So what went wrong actually? Now I just need to do this presentation. I have 10 minutes, right? Something like that?
Yeah.
Yeah, so a lot of these errors were import errors, which in Python means that you have a dependency that you haven't solved. So this is a description of dependency hell. So your code depends on someone else's code, that depends on someone else's code, that depends on someone else's code, and I can stand here all day saying that, you know. So that is the problem that we would like to address. So when I arrived here at Stanford, I received this. These are my dependencies. Obviously, I can make this work, right? I'm going to be here for 2 years. It's fine. But it took me maybe a day to sort this out. You have to have the right version that can run together with another version, etc. So how can you document these dependencies? A lot of people in this room know this, but you can use something like Docker, for example, to document your dependencies. So Docker is a container, which is an isolated environment. So I think of it as sort of like a lightweight version of a virtual machine. So giving someone a container is like giving them your computer, basically, not your whole computer, like maybe not your documents folder, but it solves the dependency problem. And it also has the advantage that it can be deployed to servers and easily run remotely, which can be useful. Not for me so much. I don't use Docker that much, but I know people who swear by it. So who here has used Conda? Everybody. Okay, so I'm preaching to the choir. It's an open source cross-platform package management thingy, and it manages environments, right? So you can create and load and switch between these different software environments. The problem I have with Conda is that I often forget or confuse which environment I have used for which project. So I have a lot of projects, I have a lot of environments, and I need to switch between them, and I just find it annoying. So the people who made Conda have recently made something called Pixie, and it's sort of like the logical continuation of Conda. It's an easy environment and package management thing on a project level. So it lives in the folder where you have all your project files because you have a very organized structure in your folders, right? I don't know what this is. Is it supposed to be a block of cheese? I'm not sure. So I think of Pixie as something that, like, it's a bit like Docker because I have everything I need in the folder, but it doesn't have the overhead that Docker has. So how do you Pixie? Well, it's a bit like GitHub. You use Pixie init, it creates a folder, and then you go into it, and you can add all your dependencies. You can also edit the file, of course. So this is the pixie.toml file that describes exhaustively which of these dependencies I need in my project. So with this, my project is reproducible. And if I want to, so I can put pixie.toml in a directory. I can go into that directory and I can write pixie install, and it just downloads all the dependencies. So it's live demo time. So I have a little toy project that I worked on. Not this one. That I made a little sort of like a toy block simulator that uses WGPU. How many knows about WGPU or Web GPU? Carlos, nice. It's a successor of OpenGL. So I just wanted to render using OpenGL. So I'm gonna open this folder. I'm gonna take the line renderer, which I need. This is the simulator. This is the Pixie toml file, and this is the magnetization vector class that I made. I'm gonna copy these. I'm gonna go here, make a new folder, Pixie demo. Right, where's paste? There. Okay. So I put those there, new terminal folder, and then I'm gonna make it a bit bigger so you can see. Can anyone see? Everyone see? Sorry. Yeah, so here we are. We can check what's in this pixie.toml file. So it has all the dependencies here. They're not many.
Do you have to put the versions in yourself, or does it?
No, it does that automatically. Yeah. But you can also edit this file. That's how I do it. But you can also do Pixie add, and yeah. So I can also do Pixie info, and I get basically the same info. So this is where Pixie lives on my computer. This is the name of the project, just a bit random. So I can just do pixie install. And it just installed all the everything. So I can try running simulator. I should have done this before I did the pixie install, but so this is the default Python environment in my computer, right? Doesn't work because it doesn't have WGPU. So then I can do pixie run. So now it knows that I'm going to run Python in this folder. Oh, the suspense. Oh, it works. Very relaxing. Yeah, so I think that like if there's anything I want you to bring with you from this talk is how to do this. And this, I think this is a wonderful tool. And I think it's well, newer programming languages have this sort of built in, but I think everybody's going to be using Python for at least 10 years. So yeah. Let's see. I also planned to talk about Git. How many of you use Git? Everybody, okay, so you know how that works. Am I out of time? I think so, right?
You're good.
I'm good? Okay. Okay, so this, I mean, how do we address this? Hyper competition and pressure and wrong incentives. I don't know what to say, really. I mean, sure, it's competitive. Everything is. I'm not sure what they mean when they created this Venn diagram. Will competition make people sloppy? Maybe. I don't know. Wrong incentives. I don't know. I think you should, as a scientist, have a commitment to the truth. I don't know. I mean, this is a little bit like it feels to me like an accusation. I don't know. But this is not really something I can change. Yeah.
Well, I think it's also referring to the fact that we are incentivized to publish more papers, but not papers that are necessarily the extra step of making sure that it runs or it just works for the paper, and then that's it.
Yeah. True. I think this is we could discuss this all day, and we will discuss it at Fika today. Oh, but I mean, it's interesting, right? Publish or perish. Yeah.
I have a recommendation in case anybody is interested. I don't know if people are familiar with the Stanford prison experiment by Zimbardo. There was a documentary that came out last year about how basically everything that was claimed, and he wrote all these books about it, and he's still celebrated, but how all of this is based on a lot of manipulation that has been unpublished. So there was a guy that took years of work to dig into the archives of the materials that they had actually written down in the basement, and he kind of published about it, and then they made this documentary out of it. So that is an example of this, I guess, because this guy published a lot of books.
Are you meaning that Philip Zimbardo is his name, I think?
Yeah.
That he was. Yeah, I mean, a lot of people that have there's not that many accounts. I don't know about this specific case, but I think there is one book by a guy who actually fabricated a bunch of data where he talks about why he did it. That's kind of rare because these people disappear, you know, they don't want to be in the limelight anymore, and what caused them to do it. And yeah, for anyone, I'm going to try and dig that up. I think that would be an interesting discussion point. Like, what actually drives people? Are they psychopaths? I don't know. I don't think that's a useful analysis, really. Okay, so I was going to talk about the FAIR principles, which is something that's kind of popular in this field. It's where it's a set of principles that mean that what you do should be findable, accessible, interoperable, and reusable. But I think that's so boring, so I'm just gonna switch to the last one of these. So anyone give me 2 sets of coordinates? It's a little tricky. It's trickier than the one before.
D6 and
D6, yeah.
C9-ish.
Oh, well, yeah, very good. Yes, true.
D6 and D9.
Almost a square.
C9 and D9.
Yeah.
So I just put some alpha in there. Nice. Yeah, okay. So I originally had 5 selfless reasons to work reproducibly, but I don't think we have time for that. So I'm going to end with my sort of, I have a dream speech. I have a dream for science that is open, transparent, and accessible to all. A dream where we don't just publish papers, but also share the data, methods, and tools that lead to our conclusions. I don't think anybody would necessarily run everything, but I think if just that everybody knows that you can, would reduce sloppy and fraudulent behavior in science. Yeah, that's it. Thank you.
Part 3 next.
Sorry, I'm sure I have to do some actual work. Yeah.
Killed with.
Sorry? Oh, thank you.